The soft landing of India's Chandrayaan-3 spacecraft near the lunar South Pole on August 23, 2023, marked more than just a technological triumph for the Indian Space Research Organization. As the Vikram lander touched down and the Pragyan rover began its careful traverse across the ancient regolith, scientific instruments aboard started returning data that would challenge and refine our understanding of Earth's celestial companion. Among the most striking revelations was the unambiguous detection of sulfur in the lunar soil, a finding that carries profound implications for how we think about the moon's chemical evolution and its potential as a destination for sustained human presence. The discovery came from the laser-induced breakdown spectroscopy instrument mounted on the Pragyan rover. This sophisticated device works by firing focused laser pulses at the lunar surface, creating tiny plasma clouds where the intense energy vaporizes microscopic amounts of material. As the plasma cools, it emits light at wavelengths characteristic of the elements present. By analyzing this spectral signature, scientists can determine the chemical composition of the target with remarkable precision. What made the sulfur detection particularly noteworthy wasn't simply its presence, but rather the direct, in situ confirmation using this technique. Previous missions had suggested sulfur might exist in lunar soils through remote sensing and sample analysis, but the Chandrayaan-3 measurements provided unequivocal evidence right there on the surface, without the complications of sample return or the uncertainties of orbital observations. Sulfur's presence on the moon tells us something fundamental about the violent processes that shaped our satellite and the broader story of planetary formation. The leading theory for the moon's origin involves a catastrophic collision between the early Earth and a Mars-sized body scientists call Theia. This impact, occurring roughly 4.5 billion years ago, would have generated temperatures so extreme that rock vaporized and metals melted into a spinning disk of debris around our planet. From this infernal maelstrom, the moon coalesced. Conventional wisdom held that such extreme heat would have driven off volatile elements, those substances that vaporize at relatively low temperatures. Sulfur falls into this category, with a boiling point far below that of the silicate minerals that make up most of lunar rock. Yet there it sits, detected clearly in the measurements from Chandrayaan-3. This finding forces us to reconsider either the conditions during the moon's formation or the subsequent processes that delivered sulfur to the surface. Perhaps pockets of the proto-lunar disk cooled faster than models predicted, allowing some volatiles to condense and incorporate into the forming moon. Alternatively, sulfur might have arrived later through bombardment by comets and asteroids, those icy wanderers and rocky messengers that crisscross the early solar system. Each possibility opens different windows into understanding not just the moon's history, but the dynamics of planet formation everywhere. The distribution and abundance of sulfur also matters for practical reasons that extend beyond pure science. Future lunar bases will need resources, and sulfur is surprisingly useful for space applications. Combined with other elements abundant on the moon, sulfur could be part of manufacturing processes for construction materials. Sulfur concrete, for instance, has been proposed as a building material that doesn't require water, a precious commodity on the airless moon. The element also plays roles in certain types of energy storage systems and could be part of chemical processes for extracting oxygen from lunar minerals. Understanding where sulfur concentrates and in what chemical forms it exists becomes crucial for planning sustainable lunar operations. The Chandrayaan-3 landing site near the lunar South Pole was chosen deliberately for several strategic and scientific reasons. This region experiences unique lighting conditions, with some areas receiving nearly constant sunlight, while nearby craters remain in perpetual shadow. These permanently shadowed regions are cold enough to trap water ice and other volatiles for billions of years, making them targets of intense interest for both scientific study and resource prospecting. The boundary between light and shadow, where Chandrayaan-3 operates, provides access to both environments. The sulfur detection in this region raises questions about whether the element's abundance varies with latitude or proximity to these cold traps, and whether some portion might be associated with volatile deposits rather than being locked in mineral structures. Beyond sulfur, Chandrayaan-3's instruments have been gathering data on a suite of other elements present in the lunar regolith. The measurements include aluminum, calcium, iron, chromium, titanium, manganese, silicon, and oxygen. so essentially confirming the general picture of lunar composition built up over decades of study, while providing new details about how these elements vary at small scales across the landing site. Each element tells part of the story about the rocks from which the soil derives and the processes that have mixed and altered that soil over eons of meteorite impacts, solar wind bombardment, and thermal cycling. Iron's presence in various oxidation states provides clues about the oxygen fugacity, essentially how oxygen-rich the environment was when minerals formed. Titanium abundance connects to the types of basaltic lava that erupted from the lunar interior and flooded vast plains billions of years ago. Chromium and manganese exist in trace amounts, but their ratios to other elements help distinguish between different source rocks. Silicon and oxygen together make up the silicate framework of most lunar minerals, while aluminum appears concentrated in plagioclase feldspar, a mineral component that dominated the Moon's earliest crust. This ancient crust, formed as lighter minerals floated to the top of a global magma ocean, still covers the lunar highlands and provides a record of the satellite's primordial differentiation. The detection methodology itself represents an elegant solution to the challenge of analyzing alien soils without a full laboratory: the laser-induced breakdown. Spectroscopy unit on Pragyan operates in an environment far harsher than any terrestrial laboratory. Temperatures swing from well above boiling to far below freezing as the sun rises and sets over the 2-week lunar day. There's no atmosphere to moderate these extremes or to scatter light in familiar ways. Dust, electrostatically charged by solar radiation, behaves differently than Earth dust, potentially coating surfaces and interfering with measurements. Yet the instrument continued to function, firing its laser, collecting spectra, and transmitting data back through the Vikram lander to Earth. And this kind of in-situ analysis offers advantages that complement both remote sensing from orbit and laboratory analysis of return samples. Orbital instruments can survey vast areas, but must interpret surface composition through layers of atmosphere or across tens or hundreds of kilometers of space, introducing uncertainties. Return samples provide exquisite detail, but only for the tiny fraction of the Moon that has been sampled, and they may be altered during collection and return. Direct surface measurements split the difference, examining materials in their original context with good precision, though limited to wherever the rover can reach. Together, these approaches build a comprehensive picture, each filling gaps left by the others. The second major revelation from Chandrayaan-3 involves signatures suggesting the presence of lunar mantle material at or near the surface. The Moon, like Earth, differentiated early in its history into layers of distinct composition. The lightest materials rose to form the crust, while denser materials sank toward the center, forming a mantle and possibly a small metallic core. The mantle, which comprises the bulk of the Moon's volume, is thought to consist of minerals rich in magnesium and iron, specifically olivine and pyroxene. These minerals have been detected in lunar samples and from orbit, but they're generally associated with volcanic rocks that erupted from the interior or with lower crustal materials exposed by impacts. What makes the Chandrayaan-3 observations particularly intriguing is the suggestion that mantle materials might be more accessible near the South Pole than previously recognized. Several large impact basins scar the lunar surface, ancient collisions so powerful they punched through the crust and excavated material from depth. The South Pole Aitken Basin, the largest and oldest of these features, stretches across the far side and southern reaches of the Moon. This enormous depression, roughly 2,500 kilometers in diameter and up to 13 kilometers deep in places, certainly penetrated deep into the lunar crust and possibly into the mantle itself. Material thrown out during its formation would have spread across surrounding regions, potentially delivering mantle fragments to areas far from the impact point. Identifying mantle material requires distinguishing it from crustal rocks and from the mare basalts that erupted long after the Moon's initial layering. Mantle rock should have distinctive chemical and mineralogical signatures, being richer in magnesium relative to iron compared to most crustal rocks, and having different ratios of certain trace elements. The spectroscopic data from Chandrayaan-3, combined with careful analysis of mineral types and compositions, points toward components in the South Polar regolith that match expectations for mantle-derived material. And this interpretation aligns with observations from orbital missions that detected similar signatures in the South Pole Aitken Basin and surrounding highlands. Confirming the presence of mantle material at accessible locations would be scientifically invaluable. The lunar mantle has never been directly sampled. Apollo missions brought back pieces of crust and volcanic rocks, but nothing definitively from the deep interior. Even meteorites from the moon, ejected by impacts and occasionally falling to Earth, typically represent surface or near-surface materials. Accessing mantle rocks would provide a window into the moon's bulk composition and the processes that separated it into layers. These rocks would carry information about temperatures and pressures in the deep interior, about the minerals stable under those conditions, and about the chemical evolution that occurred as the moon cooled and solidified from its initial molten state. The composition of the lunar mantle also constrains models of how the moon formed from the debris of the giant impact between Earth and Theia. Different scenarios for that collision predict different abundances of elements in the final product. If most of the moon came from Theia rather than Earth, the isotopic signature should differ from terrestrial rocks in measurable ways. If the debris mixed thoroughly before the moon coalesced, the isotopes should match closely. Current measurements show striking similarities between Earth and lunar samples for many isotope systems, suggesting thorough mixing. But questions remain about exactly how the impact unfolded and whether some isotopic differences might appear in materials from the deep interior that haven't been sampled yet. Temperature plays a role in this story that extends beyond the formation event itself. The moon has been cooling for billions of years, and that thermal evolution left records in the rocks. Early in its history, heat from the giant impact, from gravitational compression, and from radioactive decay kept the interior molten or partially molten. The magma ocean eventually crystallized, with different minerals forming at different depths as temperatures dropped. The sequence of crystallization is recorded in the distribution of elements between minerals and in the overall structure of the mantle. Some elements preferentially enter certain minerals, so as those minerals solidify and settle or float, they carry those elements with them, creating chemical variations with depth. Later, as the interior continued to cool but remained warm enough for convection, mantle rocks slowly flowed, driven by temperature differences. Hotter, less dense material rose, while cooler, denser material sank, mixing the interior and transporting heat outward. This convection might have operated differently in the moon compared to Earth because of the moon's smaller size and faster cooling. So, understanding lunar mantle composition helps scientists model this thermal history and compare it to processes in other rocky bodies across the solar system. Every planet and large moon went through similar early differentiation, but the details varied based on size, composition, and impact history. The presence of mantle material near the surface also raises questions about the impact that exposed it. The South Pole Aitken Basin formed early in lunar history, probably during the first few 100 million years after the moon's creation, an era known as the Late Heavy Bombardment, when impacts were far more frequent than today. The impactor that created this basin must have been enormous, perhaps 100 kilometers or more in diameter, striking at tens of kilometers per second. The energy release would have been unimaginable, melting and vaporizing rock across a vast area, creating a splash of ejecta that spread around the moon and leaving a depression that still dominates the southern hemisphere. Over time, subsequent impacts have gardened the soil around the South Pole Aitken Basin, mixing ejecta with local materials and complicating attempts to identify what came from where. The regolith, that layer of broken rock and dust covering all lunar surfaces, contains fragments from near and far, each grain a piece of a complex puzzle. Sorting out which grains represent mantle material, which come from local crust, and which were delivered from impacts elsewhere requires careful analysis. The instruments on Chandrayaan-3 provide one line of evidence, but connecting that to the broader story involves integrating observations from orbit. Laboratory studies of Apollo samples, modeling of impact processes, and geological mapping of the surface. Geological mapping on the moon relies heavily on imagery and spectroscopy from orbit. Different rock types reflect sunlight differently, with variations in brightness and color revealing mineral composition. Impact craters serve as windows into the subsurface, excavating buried layers and spreading them on the surface where instruments can detect them. The age of surfaces can be estimated by counting craters, since older surfaces have accumulated more impacts over time. Combining these techniques, scientists have built detailed maps showing the distribution of rock types, the locations and ages of volcanic flows, and the structure of major impact basins. And these maps guided the selection of the Chandrayaan-3 landing site and help interpret the measurements returned by the mission. Knowing the geological context, the types of terrain surrounding the landing area, and the history of impacts in the region allows scientists to generate hypotheses about what the rover should find and then test those predictions against the actual data. When observations match predictions, confidence grows that the geological models are correct. When surprises emerge, like unexpected abundances or unusual mineral signatures, they point toward gaps in understanding that drive new research. The technology enabling these discoveries has advanced dramatically since the early days of lunar exploration. The Apollo Lunar Surface Experiments packages, deployed by astronauts between 1969 and 1972, were marvels of their time, but limited by the electronics and power systems available. Modern instruments pack far more capability into smaller packages. Spectrometers have better resolution and can detect fainter signals. Computers process data on board, reducing the volume that must be transmitted to Earth. Power systems, whether solar panels or radioisotope generators, provide more energy more reliably. Communication systems handle higher data rates across the vast distance between Earth and Moon. Chandrayaan-3 benefits from decades of technological development and learning from previous missions, both successful and otherwise. The mission incorporates lessons from Chandrayaan-2, which successfully placed an orbiter around the Moon, but saw its lander crash during the descent attempt in 2019. Engineers studied what went wrong. They improved the landing algorithms, added redundancy to critical systems, and tested extensively. The result was a flawless landing that placed the Vikram lander precisely in its intended location, allowing Pragyan to begin its traverse across carefully selected terrain. This success demonstrates India's growing capabilities in space exploration and sets the stage for more ambitious missions in the future. The findings from Chandrayaan-3 have already begun to reshape our understanding of the Moon in ways that scientists didn't fully anticipate. While the mission objectives included surface composition analysis, the discovery of sulfur in significant quantities near the lunar South Pole has opened up new avenues of scientific inquiry. So the Pragyan rover carried a suite of instruments designed to analyze the chemical composition of the regolith, and what it found has sparked intense discussion in the planetary science community. Sulfur on the Moon isn't entirely unexpected in theory, but detecting it in measurable concentrations at the surface level provides concrete evidence that changes how we think about lunar chemistry. Previous missions had suggested the presence of sulfur compounds, but Chandrayaan-3's instruments confirmed it through direct contact with the surface material. The alpha particle X-ray spectrometer aboard Pragyan identified sulfur signatures that indicate this element is more widespread in the polar regions than earlier models predicted. This matters because sulfur can tell us about volcanic processes, impact events, and the chemical evolution of the lunar surface over billions of years. Understanding why sulfur is present in these concentrations requires looking at multiple processes that have shaped the Moon. Volcanic activity in the Moon's early history would have released sulfur-bearing gases that eventually settled on the surface. Impact events from asteroids and comets, many of which contain sulfur compounds, would have contributed additional material. The key question becomes whether the sulfur detected by Chandrayaan-3 comes primarily from ancient volcanic deposits, from external bombardment, or from some combination of both. Each scenario has different implications for how we reconstruct the Moon's geological timeline. The South Polar region where Vikram landed sits within a unique geological context. This area has remained in shadow for much of its existence, creating permanently shadowed craters that act like cold traps, preserving volatile compounds that would otherwise escape into space. The temperatures in these shadowed regions can drop to incredibly low levels, making them ideal storage areas for materials that would be unstable elsewhere on the lunar surface. When Pragyan analyzed samples from areas adjacent to these permanently shadowed regions, the sulfur signatures suggested that some of this element might have migrated from the cold traps or been deposited through processes linked to the extreme temperature gradients in the area. What makes the sulfur discovery particularly intriguing is its potential connection to water ice. Scientists have long suspected that the permanently shadowed craters at the lunar poles contain substantial deposits of water ice mixed with regolith. The presence of sulfur in the same general region raises questions about chemical interactions between these compounds. In cold environments, sulfur can form various compounds with hydrogen and oxygen, potentially creating sulfuric acid ice or other exotic materials that don't exist in more temperate regions of the Moon. These chemical species would have significant implications for any future human missions attempting to extract and utilize lunar resources. The practical applications of finding sulfur shouldn't be overlooked. For future lunar bases, having access to sulfur means having access to a resource that could be used in various industrial processes. Sulfuric acid can be synthesized and used in chemical processing, while elemental sulfur could potentially be incorporated into construction materials or used in manufacturing processes. The Moon's harsh environment demands that any sustained human presence make maximum use of local resources rather than relying entirely on supplies shipped from Earth. Every element found in accessible quantities represents one less thing that needs to be transported across hundreds of thousands of kilometers. Beyond the sulfur findings, Chandrayaan-3 has contributed to another mystery that has planetary scientists reconsidering their models of lunar formation. Evidence suggesting the presence of materials from the lunar mantle has emerged from the data being analyzed. The Moon's mantle lies beneath its crust, and under normal circumstances, we wouldn't expect to find mantle material exposed at the surface. The fact that Chandrayaan-3's instruments detected signatures consistent with mantle composition indicates that some extraordinary process has brought this deep material to where the Pragyan rover could analyze it. The leading explanation involves massive impact events that excavated material from deep within the Moon's interior. When large asteroids or comets slam into a planetary body with sufficient energy, they can punch through the crust and eject material from the mantle layers below. The South Pole Aitken Basin, one of the largest and oldest impact structures in the solar system, sits in the general region where Chandrayaan-3 conducted its mission. This enormous impact basin measures roughly 2,500 kilometers in diameter and could have excavated material from depths that would otherwise remain forever hidden from surface exploration. If the material Pragyan analyzed truly comes from the lunar mantle, it provides a rare opportunity to study the Moon's interior composition without drilling deep boreholes or relying entirely on seismic data. The mantle represents the layer where much of the Moon's early differentiation occurred, the process by which heavier elements sank toward the center while lighter materials rose to form the crust. Understanding mantle composition helps scientists reconstruct how the Moon evolved from a molten sphere into the layered body we observe today. And the chemical signatures that suggest mantle material include elevated concentrations of certain elements that are typically depleted in crustal rocks, but enriched in the mantle. Magnesium-rich minerals and specific ratios of iron to magnesium provide clues about the depth from which material originated. The instruments aboard Pragyan weren't designed specifically to identify mantle material, which makes this finding even more remarkable. It demonstrates that sometimes the most important scientific discoveries come from careful analysis of data that initially seemed routine. Confirming that surface materials truly originated from the mantle requires careful comparison with theoretical models and with samples from other missions. The Apollo missions brought back rocks from various lunar locations, and scientists have spent decades analyzing their composition. However, the Apollo landing sites were selected partly for safety reasons, which meant they sampled relatively flat, geologically stable regions. The South Polar region where Chandrayaan-3 landed represents a different geological environment, one shaped by massive impacts and unusual preservation conditions. Comparing the Chandrayaan-3 data with Apollo samples helps distinguish between crustal and mantle signatures. The presence of mantle material at the surface also relates to questions about the Moon's formation through the giant impact hypothesis. This theory proposes that the Moon formed from debris ejected when a Mars-sized object collided with the early Earth. The impact would have melted and vaporized enormous amounts of material, which then coalesced in orbit to form the Moon. If this scenario is correct, the Moon's interior should preserve chemical signatures from both the impacting body and Earth's early mantle. Finding mantle material at the lunar surface gives scientists a chance to test predictions from impact models against actual measurements. Temperature measurements from the landing site have added another layer of understanding to the mission's achievements. The Vikram lander carried instruments to measure how temperature varies with depth below the surface. These measurements revealed unexpected temperature gradients that don't match the predictions from previous thermal models. The regolith, the layer of loose, fragmented material covering solid bedrock, conducts heat differently than scientists had calculated based on earlier missions. This discovery affects everything from planning safe landing sites to designing habitats that can protect astronauts from extreme temperature swings. During the lunar day, which lasts about 2 weeks of Earth time, surface temperatures can soar well above the boiling point of water. When night falls, temperatures plummet to incredibly cold levels. This extreme temperature cycling affects how materials behave and how much energy would be needed to keep equipment or habitats at stable temperatures. The data from Vikram showed that temperatures drop off more rapidly with depth than expected, suggesting that the regolith has different insulating properties than previous models assumed. This finding will directly influence the design of future surface infrastructure. The rover's mobility system also provided valuable engineering data. Moving across the lunar surface isn't as straightforward as driving a vehicle on Earth. The reduced gravity, the lack of atmosphere, and the properties of the regolith all affect how a rover interacts with the terrain. Pragyan encountered various surface conditions during its traverse, from fine dust to larger rocks, and the way it handled these obstacles provides engineers with real-world data to improve future rover designs. Each wheel rotation, each turn, each navigation decision by the onboard systems adds to the knowledge base that will inform the next generation of lunar explorers. One of the challenges in interpreting Chandrayaan-3's findings comes from the limited context available from previous missions to this specific region, and the south polar areas of the Moon remain among the least explored territories in the solar system. While orbital missions have mapped the surface from above, there's no substitute for direct surface contact when it comes to understanding fine details of composition and physical properties. Chandrayaan-3 represents only the second mission ever to land in this region, following Russia's Luna 25, which unfortunately crashed before completing its mission. This scarcity of ground truth data means that every measurement Pragyan makes carries extra weight in the scientific community. The mission has also contributed to our understanding of the space environment around the Moon. Instruments aboard Vikram measured the plasma environment, the thin envelope of charged particles that surrounds the Moon. Unlike Earth, the Moon lacks a global magnetic field and substantial atmosphere, which means it interacts directly with the solar wind, the stream of charged particles flowing outward from the Sun. Understanding this interaction helps scientists predict how spacecraft systems will behave in the lunar environment and how solar activity might affect operations on the surface. Radiation measurements from the landing site provide crucial data for planning human missions. Astronauts on the lunar surface will be exposed to radiation from cosmic rays and solar events without the protection of Earth's atmosphere and magnetic field. The measurements from Chandrayaan-3 help refine models of radiation exposure and inform the design of protective shielding for habitats and spacesuits. While the mission wasn't specifically designed for extended radiation monitoring, the data collected during the approximately 1 lunar day of operations adds valuable points to the growing database of environmental measurements. The scientific community has responded to Chandrayaan-3's findings with a mixture of excitement and careful skepticism, which is exactly how science should proceed. Extraordinary claims require extraordinary evidence, and while the initial data looks promising, researchers are working to verify the findings through multiple independent analyses. Peer review processes ensure that interpretations are scrutinized by experts who can identify potential alternative explanations or systematic errors in the data. This process takes time, but it's essential for building reliable scientific knowledge. International collaboration has played a role in analyzing the mission data. Space agencies and research institutions around the world have expressed interest in accessing Chandrayaan-3's findings to compare with their own datasets. NASA's Lunar Reconnaissance Orbiter, which has been mapping the Moon from orbit since 2009, can provide complementary observations of the landing site region. The European Space Agency, China's space program, and various academic institutions bring different expertise and perspectives that enrich the interpretation of results. This collaborative approach accelerates scientific progress and ensures that findings are robust across different analytical methods. The technological demonstrations from Chandrayaan-3 extend beyond the scientific instruments. The mission showcased India's capabilities in precision navigation and landing, areas that are critical for any ambitious space exploration program. The ability to target a specific landing site and arrive there safely opens possibilities for future missions to even more challenging locations. Landing in permanently shadowed craters, for instance, would require even more sophisticated navigation and hazard avoidance systems, but the technologies demonstrated by Chandrayaan-3 provide a foundation for such advances. Communication systems performed flawlessly throughout the mission, maintaining contact with Earth despite the challenging geometry of the South Polar location. When landing sites are at extreme latitudes, there are times when direct communication with Earth is difficult or impossible. Chandrayaan-3 used a combination of direct-to-Earth communication and relay through its orbiter to ensure continuous data flow. This approach will likely be adopted by future missions to polar regions, potentially leading to the establishment of a dedicated communication relay infrastructure around the Moon. The rover's autonomous operation demonstrated advances in artificial intelligence and machine learning applied to space exploration. Pragyan couldn't rely on real-time commands from Earth for every decision, given the communication delay and the need to respond quickly to obstacles or opportunities. Instead, it operated with a degree of autonomy, analyzing its surroundings and making navigation decisions within predefined parameters. This capability becomes increasingly important as missions venture to more distant locations where communication delays make real-time control impractical. Power generation and management during the mission highlighted both achievements and challenges. The lander and rover relied on solar panels to generate electricity, which works well during the lunar day when sunlight is available. However, the lunar night presents a harsh challenge with no sunlight for energy and temperatures that can damage electronic systems. Chandrayaan-3 was not designed to survive the lunar night, and as expected, operations ceased when darkness fell over the landing site. So future missions aiming for extended operations will need to incorporate alternative power sources such as radioisotope thermoelectric generators or advanced battery systems that can store enough energy to last through the 2-week night. The cost-effectiveness of Chandrayaan-3 has drawn attention from space agencies and commercial entities looking to conduct lunar missions on reasonable budgets. India's space program has developed a reputation for achieving impressive results with relatively modest funding compared to other major space programs. This efficiency comes from careful engineering, leveraging existing technologies where appropriate, and maintaining a focused mission scope rather than trying to accomplish everything in a single mission. The approach demonstrates that meaningful lunar exploration doesn't necessarily require budgets that only the wealthiest nations can afford. The mission's success has energized India's space program and boosted national pride, much as the Apollo missions did for the United States, or as China's recent lunar achievements have done. Space exploration serves purposes beyond pure science, providing inspiration and demonstrating technological capabilities that have spillover effects in other sectors. The engineers and scientists who worked on Chandrayaan-3 have gained experience and expertise that will benefit future missions and potentially contribute to terrestrial applications of space technology. Looking at the broader context of lunar exploration, Chandrayaan-3 fits into an emerging pattern of renewed interest in the Moon from multiple nations and commercial entities. The Artemis program aims to return humans to the lunar surface, while China has announced plans for a lunar research station. Commercial companies are developing lunar landers and rovers for various purposes. This surge of activity transforms the Moon from a destination visited briefly during the space race into a location of sustained interest and presence. Chandrayaan-3's contributions to our scientific understanding of the Moon enhance the collective knowledge base that all these efforts can draw upon. The sulfur detection has prompted theoretical work on the chemical history of the lunar surface. Researchers are developing new models that incorporate sulfur-bearing compounds into the complex web of chemical reactions and physical processes that have shaped the Moon. These models need to account for the extreme temperature variations, the constant bombardment by micrometeorites, the effects of solar wind particles, and the occasional larger impacts that can dramatically alter local conditions. Getting the chemistry right is essential for predicting where valuable resources might be found and how they might be extracted and processed. Some scientists have proposed that sulfur could be linked to ancient volcanic vents or fumaroles where gases escaped from the lunar interior. If such features exist in the South Polar region, they would represent remnants of a more geologically active past. The Moon today is largely dormant, with no active volcanism or tectonic activity, but billions of years ago, it was a much more dynamic world. Identifying the signatures of ancient volcanic activity helps scientists reconstruct the thermal evolution of the Moon and understand when and why it transitioned from an active body to the quiet world we observe today. The detection of potential mantle material has inspired proposals for follow-up missions specifically designed to study the composition and structure of the lunar interior. Some concepts involve deep drilling to directly sample layers beneath the surface, while others propose more sophisticated instruments that could analyze samples with greater precision than Pragyan's instruments allowed. Understanding the lunar interior isn't just an academic exercise. It relates directly to fundamental questions about planetary formation and differentiation processes that apply throughout the solar system and beyond. The relationship between the Moon's interior structure and its surface features becomes clearer with each new piece of data. The South Pole Aitken Basin, if it truly excavated mantle material, represents a natural window into the Moon's interior. Studying this region in detail could reveal more about the layering of different materials, the depth at which the mantle begins, and how composition varies with depth. These insights would then inform models of the giant impact that formed the Moon, potentially constraining parameters like the size and velocity of the impacting body and the state of the early Earth's mantle. Comparing lunar science with the study of other planetary bodies highlights how each world presents unique challenges and opportunities. Mars has an atmosphere that affects landing dynamics and surface chemistry, while asteroids have such low gravity that landing on them requires completely different approaches. The Moon occupies a special position as the most accessible major body beyond Earth, close enough for relatively quick travel, yet still presenting the challenges of operating in a hostile space environment. Lessons learned from lunar missions like Chandrayaan-3 directly apply to planning missions to more distant destinations. The educational impact of Chandrayaan-3 extends throughout India and internationally. Students studying planetary science, engineering, and/or related fields can point to this mission as a real-world example of how scientific knowledge grows through observation and analysis. The mission provides case studies for courses on spacecraft design, mission planning, instrument development, and data analysis. Beyond formal education, the mission has captured public imagination, encouraging young people to consider careers in science and technology. This inspirational aspect of space exploration, while harder to quantify than scientific results, plays a crucial role in building the workforce that will tackle future challenges. Media coverage of the mission has ranged from detailed technical analyses in scientific publications to general interest stories highlighting the achievement. This variety of coverage reflects different audiences and purposes, but all contribute to public awareness of space exploration. When scientific missions receive public attention, it helps justify the investment of resources and maintains political support for continued exploration. The challenge lies in communicating complex scientific findings in ways that are accurate yet accessible to non-specialists. Chandrayaan-3's relatively straightforward objectives and dramatic landing success made it easier to tell compelling stories while still conveying substantive information. The media coverage itself provides an interesting case study in how different audiences engage with space exploration. Technical journals focused on measurement precision and methodological innovations. Mainstream news outlets emphasize the national achievement and competitive aspects. Educational platforms use the mission as a teaching opportunity for students learning about planetary science. Social media created a more immediate and personal connection, with people sharing their excitement as events unfolded. Each of these channels served different purposes, but collectively contributed to making Chandrayaan-3 a cultural moment beyond its scientific importance. International collaboration in analyzing the findings demonstrates how modern science transcends national boundaries, even when missions are nationally run. Scientists from various countries have contributed their expertise in interpreting the data, comparing it with findings from other lunar missions, and integrating it into broader theoretical frameworks. This collaborative spirit reflects the reality that understanding complex systems like the Moon requires pooling knowledge and perspectives from diverse sources. While nations may compete in launching missions, the scientific community generally operates with a more cooperative ethos focused on advancing collective understanding. The sulfur detection has prompted interesting questions about the chemistry of space weathering on the Moon. Space weathering refers to the gradual changes that occur to exposed surfaces due to micrometeorite impacts, solar wind bombardment, and radiation exposure. These processes can alter the chemical state and distribution of elements on the surface. Understanding how sulfur compounds respond to space weathering helps refine models of how the lunar surface evolves over geological time. It also has implications for interpreting data from other airless bodies in the solar system that undergo similar weathering processes. Research into volatile elements like sulfur connects to broader questions about how volatiles are distributed throughout the solar system. Volatiles are substances that evaporate easily at relatively low temperatures, and their presence or absence in different locations tells us about the conditions during planetary formation and subsequent evolution. The traditional model suggested that the inner solar system was largely depleted of volatiles due to the heat from the forming sun. Finding sulfur and potentially other volatiles at various lunar locations suggests a more complex picture where local conditions, delivery mechanisms, and retention processes all played roles in determining the final distribution. The technological achievements of Chandrayaan-3 extend beyond the immediate scientific findings. The mission validated navigation systems, landing algorithms, communication protocols, and surface operation procedures that will inform future missions. Each successful landing adds to the collective knowledge base about how to safely reach and operate on the lunar surface. The specific challenges of landing in the South Polar region, with its varied terrain and lighting conditions, provided valuable experience that will benefit not just Indian missions, but the broader spacefaring community as future missions target similar locations. Temperature measurements from the lunar surface provided by Chandrayaan-3 have refined our understanding of the extreme thermal environment. The surface experiences dramatic temperature variations from intensely hot during the lunar day to extremely cold during the lunar night. Understanding these temperature profiles is essential for designing equipment that can survive and operate in such conditions. The measurements also contribute to understanding heat flow from the lunar interior, which provides clues about the Moon's internal structure and thermal evolution. Every new data point helps constrain models and reduce uncertainties in our understanding. The detection of mantle material raises fascinating questions about the dynamics of large impact events. When massive objects strike planetary bodies, they don't just excavate material. They create conditions of extreme pressure and temperature that can transform rocks and redistribute materials in complex ways. Some models suggest that the largest impacts might have temporarily melted significant portions of the lunar crust, creating a magma ocean that then cooled and crystallized. Finding mantle material at the surface provides evidence for the violence and scale of these ancient events and helps scientists reconstruct the early bombardment history that shaped the Moon. These bombardment events weren't unique to the Moon. Earth experienced similar impacts during the same early period, but our planet's active geology has erased most of the direct evidence. The Moon serves as a record-keeper, preserving evidence of events that affected the entire Earth-Moon system. By studying the lunar surface, scientists can infer what Earth must have experienced during its formative period. This has implications for understanding how life emerged on Earth, as the timing and intensity of impacts would have influenced the conditions that early life forms encountered. The possibility of using lunar resources for producing rocket fuel represents one of the most economically significant potential applications of the sulfur discovery. Current space missions must carry all their propellant from Earth, which is enormously expensive due to the energy required to escape Earth's gravity. If propellant could be manufactured on the Moon using local resources, spacecraft could refuel there before continuing to more distant destinations. This would fundamentally change the economics of space exploration, making missions to Mars and beyond more feasible. The Moon could serve as a refueling depot, dramatically reducing the cost and increasing the scope of human activities throughout the solar system. Water ice, which likely exists in permanently shadowed craters near the poles, could be split into hydrogen and oxygen through electrolysis. Both are useful rocket propellants, and oxygen is also essential for life support. If sulfur compounds are available nearby, they could contribute to manufacturing certain types of propellant or could be used in other industrial processes supporting a lunar base. The key is finding concentrations that are economically viable to extract and process. This is where continued exploration and characterization become important, identifying specific locations where multiple useful resources exist in sufficient quantities. The engineering challenges of extracting and processing resources in the lunar environment shouldn't be underestimated. Equipment must operate in vacuum, withstand extreme temperature swings, function in abrasive lunar dust, and do all this reliably with minimal maintenance, since sending repair missions from Earth would be prohibitively expensive. The gravity is 1/6 that of Earth, which affects how materials flow and how mechanical systems behave. Power is limited and must come from solar panels or potentially nuclear sources. Every operation that seems straightforward on Earth becomes a complex engineering problem in space. Despite these challenges, the economic incentives are driving serious development efforts. Several private companies are working on technologies for lunar resource extraction, processing, and utilization. NASA's Artemis program includes components focused on demonstrating in situ resource utilization. International space agencies are collaborating on standards and protocols for lunar activities. The discovery of sulfur by Chandrayaan-3 adds another resource to the inventory of potentially useful materials, making the economic case for lunar development slightly stronger. The scientific study of sulfur on the Moon will continue long after Chandrayaan-3's active mission has ended. The data collected will be analyzed and reanalyzed as new techniques become available and as findings from future missions provide additional context. This is typical in planetary science, where datasets remain valuable for decades as scientists find new ways to extract information or make connections that weren't apparent initially. The scientific literature will include papers analyzing various aspects of the sulfur detection for years to come, each adding small pieces to the larger puzzle of lunar science. Comparative planetology benefits tremendously from missions like Chandrayaan-3. By studying multiple bodies in the solar system, scientists can identify what's universal and what's unique to particular environments. For instance, sulfur has been detected on various bodies, including volcanic moons like Io, icy moons like Europa, and now on Earth's moon. Each location has different implications for how the sulfur got there and what role it plays. Comparing these different scenarios helps scientists develop more comprehensive theories about planetary processes. The Moon serves as a relatively accessible laboratory for testing ideas that can then be applied to more distant and less accessible bodies. The educational impact of Chandrayaan-3 extends globally, not just within India. Students around the world have studied the mission as part of science curricula. The clear objectives and successful execution make it an excellent teaching example for concepts in physics, chemistry, engineering, and scientific method. When students can connect classroom learning to real-world applications like space exploration, it makes the material more engaging and memorable. Some students currently inspired by Chandrayaan-3 will become the scientists and engineers working on future missions, creating a generational continuity in space exploration. India's growing capabilities in space science have implications for geopolitics and international relations. Space exploration has always had elements of national prestige and competition, dating back to the Cold War space race. Today's landscape is more complex, with multiple nations and even private companies capable of significant achievements. India's success with Chandrayaan-3 establishes it as a serious player in lunar exploration, which brings both opportunities for collaboration and considerations about competition for resources and strategic positioning. How nations navigate these dynamics will shape the future of space activities. The legal and regulatory framework for space activities is still evolving. The Outer Space Treaty of 1967 established that celestial bodies cannot be claimed by nations, but it doesn't clearly address resource extraction. As lunar missions transition from pure science to potential commercial activities, questions about property rights, environmental protection, and equitable access become more pressing. India's lunar exploration, along with that of other nations, is taking place against this background of legal uncertainty. The practical experiences gained from actual missions will inform the development of more detailed regulations and international agreements. Environmental considerations for lunar activities might seem paradoxical since the Moon has no biosphere to protect, but scientists recognize that the lunar environment has scientific value that could be compromised by unregulated activities. And for instance, permanently shadowed craters that might contain water ice are also valuable sites for certain astronomical observations because they're extremely cold and dark. landing sites and surface operations create disturbance that could affect scientific measurements. As activity on the Moon increases, coordinating different uses and preserving sites of particular scientific interest will require planning and international cooperation. The economic potential of space resources has attracted significant private investment in recent years. Companies are developing technologies for everything from asteroid mining to lunar construction. While much of this remains speculative, the underlying economic logic is compelling. There are resources in space, and accessing them could be profitable if the technical challenges can be solved and costs reduced sufficiently. Government missions like Chandrayaan-3 contribute to this ecosystem by demonstrating technologies, characterizing resources, and inspiring the engineers and entrepreneurs who might eventually build commercial space industries. Looking at the specific characteristics of the sulfur detection, researchers are particularly interested in understanding the form in which sulfur exists. Is it elemental sulfur, or is it bound in various mineral compounds? Different forms would have different implications for both scientific understanding and potential utilization. Elemental sulfur would suggest certain chemical processes, while sulfur-bearing minerals would point to others. The spectroscopic data from Chandrayaan-3 provides clues, but fully characterizing the chemistry might require sample return missions that can bring lunar material back to Earth for detailed laboratory analysis. Sample return missions represent the gold standard for planetary science. While orbiting and landed missions can gather extensive data remotely, there's no substitute for having actual material that can be studied with the full range of analytical techniques available in terrestrial laboratories. The Apollo missions returned 842 pounds of lunar samples that scientists are still studying decades later, and those samples have fundamentally shaped our understanding of the Moon. Future sample return missions, potentially targeting regions studied by Chandrayaan-3, could bring back material containing the sulfur and potential mantle fragments that have been detected, enabling much more detailed analysis. China's Chang'e program has successfully executed sample return missions in recent years, demonstrating that this capability is not limited to the early space race era. As more nations develop sample return capabilities, we can anticipate having material from diverse lunar locations representing different geological settings. Each new sample suite will answer some questions and raise new ones, driving continued exploration. The interplay between remote sensing missions like Chandrayaan-3 and sample return missions creates a complementary approach where each type of mission informs and motivates the other. The technological development required for space missions generates spillover benefits for terrestrial applications. So technologies developed for operating in the harsh space environment often find uses in extreme environments on Earth. Materials that can withstand lunar temperature extremes might be adapted for industrial applications. Autonomous systems developed for space robotics inform terrestrial robotics. Miniaturization required for space-constrained missions benefits consumer electronics. While these spillover benefits shouldn't be oversold as the primary justification for space exploration, they're nonetheless real and contribute to the overall value proposition. The human dimension of space exploration remains compelling even as robotic missions become increasingly capable. People connect emotionally with the idea of humans venturing into space in ways that purely robotic missions don't always capture. The Artemis program's goal of returning humans to the Moon draws partly on this emotional resonance. Chandrayaan-3's findings contribute to making future human missions safer and more productive by characterizing the environment astronauts will encounter and identifying resources they might use. The relationship between robotic precursor missions and eventual human exploration has been a pattern throughout space history. India has expressed ambitions for eventually launching human spaceflight missions, including potentially crewed lunar missions in the long term. Chandrayaan-3 represents a step toward building the experience and technological base that would be necessary for such undertakings. Human spaceflight is significantly more complex and expensive than robotic missions, requiring life support systems, radiation protection, abort capabilities, and numerous other systems to ensure crew safety. The gradual accumulation of experience through missions of increasing complexity is the prudent approach that space agencies typically follow. The International Space Station Partnership demonstrates that human spaceflight can be a platform for international cooperation even among nations that have political tensions in other spheres. As lunar exploration advances, there are discussions about whether similar cooperative frameworks might develop for lunar activities. India is already part of some international coordination efforts regarding space activities. How these evolve will depend on both technical considerations and the broader geopolitical context. The potential for cooperation exists alongside the reality of competition, and the balance between these forces will shape coming decades. Chandrayaan-3's study of the lunar surface contributes to understanding the Moon's relationship with the Sun's activity. The solar wind constantly bombards the Moon, implanting atoms and molecules into surface materials. Over time, this creates a record of solar activity that scientists can read by analyzing surface and subsurface materials. Understanding this process helps with interpreting the lunar record and also informs our understanding of how the Sun's behavior has changed over time. This has implications beyond lunar science, touching on questions about solar physics and how stellar activity affects planetary environments. The Moon's lack of atmosphere means that the surface is directly exposed to cosmic radiation, including high-energy particles from outside the solar system. Understanding radiation levels at the lunar surface is crucial for planning human missions, as astronauts would need protection from this hazard. It also affects how equipment ages and degrades over time. Measurements from missions like Chandrayaan-3 contribute to characterizing the radiation environment in different lunar locations, which varies depending on factors like latitude and local magnetic anomalies. The lunar surface contains small-scale magnetic fields in certain locations, remnants of a time when the Moon might have had a more substantial magnetic field generated by internal dynamics. These magnetic anomalies affect how charged particles from the solar wind interact with the surface, potentially creating local variations in surface chemistry. Understanding these interactions helps scientists piece together the Moon's magnetic history and provides another line of evidence about its internal evolution. The relationship between magnetic fields, surface chemistry, and space weathering is complex and represents an active area of research. The discovery of sulfur adds another element to consider in these complex surface processes. Sulfur's behavior under ion bombardment, its response to micrometeorite impacts, and how it migrates or is retained in surface materials all become relevant questions. Each element behaves somewhat differently under space weathering conditions, and understanding these differences helps create more accurate models of how planetary surfaces evolve. This knowledge applies not just to the Moon, but to other airless bodies throughout the solar system. As data from Chandrayaan-3 continues to be analyzed and published, the scientific community will refine initial interpretations and potentially make additional discoveries in the dataset. Modern spacecraft generate enormous amounts of data, and thoroughly analyzing all of it takes time. Researchers might identify subtle signals or patterns that weren't apparent in the initial analysis. This is particularly true when data from multiple instruments is combined, as correlations between different measurements can reveal information that isn't evident from any single instrument alone. The success of Chandrayaan-3 has implications for India's space industry and scientific infrastructure. Success breeds confidence and attracts investment, both public and private. Students are inspired to pursue careers in space-related fields. International partners become more interested in collaboration. Research institutions gain credibility and resources. These effects compound over time, creating momentum that can sustain space programs through the inevitable setbacks and challenges that come with pushing technological boundaries. Other nations watching Chandrayaan-3's success may accelerate their own lunar programs. Space exploration often has competitive elements that drive faster progress than might occur if nations worked in complete isolation. The healthy competition to achieve firsts, to demonstrate capabilities, and to make discoveries pushes programs to innovate and take calculated risks. At the same time, the shared challenges of space exploration create common ground for cooperation. Now, the optimal approach probably involves elements of both competition and collaboration, with the balance shifting depending on specific contexts and geopolitical conditions. Commercial interest in the Moon is growing, with companies proposing everything from lunar landers to habitat construction to resource extraction. Government missions like Chandrayaan-3 help create the knowledge base that commercial ventures need. Before companies invest in lunar activities, they need to understand the environment, the availability of resources, and the technical requirements for operations. Scientific missions generate this foundational knowledge, effectively reducing risk for later commercial investments. This is a pattern familiar from terrestrial exploration, where government-funded expeditions often preceded commercial development, and the long-term vision for lunar development varies among different stakeholders. Some envision permanent research stations similar to Antarctic bases, focused primarily on science. Others see the moon as a stepping stone for deeper space exploration, a place to test technologies and establish infrastructure supporting Mars missions and beyond. Still others emphasize economic development, viewing lunar resources as having intrinsic value worth extracting. In reality, future lunar activities will likely include all these elements, with different actors pursuing different goals in a complex ecosystem of activities. The ethical dimensions of space exploration receive increasing attention as capabilities advance. Questions about planetary protection, equitable access to space resources, and the long-term sustainability of space activities all involve ethical considerations alongside technical and economic ones. How humanity conducts its first significant activities beyond Earth could set precedents that last for generations. The decisions made now about how to explore and potentially utilize lunar resources will influence the trajectory of space activities for the foreseeable future. Chandrayaan-3's sulfur detection might seem like a specific technical finding, but it connects to these broader questions. It adds to our understanding of what resources exist on the moon and where they're located. This information will inform decisions about where to establish bases, how to utilize local resources, and how to minimize environmental impact. Scientific knowledge and practical development are interconnected, with each informing the other in an ongoing process of exploration and understanding. The public imagination has long been captured by the moon, from ancient myths to science fiction, to the Apollo landings that transfixed global audiences. Each generation develops its own relationship with space exploration based on the achievements and aspirations of its time. For this generation, missions like Chandrayaan-3 are part of a renewed focus on the moon after decades when attention shifted elsewhere. Young people today are growing up during a time when lunar exploration is transitioning from occasional missions to sustained activity, potentially leading to permanent presence. The role of failure in space exploration deserves acknowledgement. Not every mission succeeds, and setbacks are inevitable when pushing technical boundaries. And India's space program experienced this directly with Chandrayaan-2's landing difficulties, making Chandrayaan-3's success particularly meaningful. The ability to learn from failures, adapt approaches, and try again is fundamental to successful space programs. The willingness to take calculated risks, knowing that not every attempt will succeed, is what enables progress in challenging technical domains. International space law and policy frameworks will need to evolve as lunar activities expand. The existing treaty framework was developed during a different era, when only 2 nations had significant space capabilities and when actual use of space resources seemed distant. Today's reality of multiple spacefaring nations and emerging commercial interests doesn't fit neatly into the old framework, and developing updated agreements that protect scientific interests, ensure equitable access, and enable beneficial use will require diplomatic effort alongside technical achievement. Missions like Chandrayaan-3 are occurring while these frameworks are still being worked out. The scientific community's approach to sharing data from space missions has evolved toward greater openness. While there are typically proprietary periods when mission teams have exclusive access to data, most space agencies eventually release data publicly so that researchers worldwide can contribute to analysis. This open science approach accelerates discovery and ensures that investments in space missions generate maximum scientific return. Chandrayaan-3's data will ultimately be available to researchers globally, enabling anyone with appropriate expertise to contribute to understanding the findings. The moon's role in Earth's environment is another fascinating area of study. The moon stabilizes Earth's axial tilt, which helps maintain relatively stable climate conditions. Tidal forces from the moon affect ocean currents and potentially even geological processes. Understanding the moon's formation and evolution is therefore relevant to understanding Earth's long-term habitability. While Chandrayaan-3's findings about sulfur and surface composition might seem removed from Earth-focused concerns, they contribute to the broader understanding of the Earth-Moon system and its evolution. As this chapter of lunar exploration unfolds, Chandrayaan-3 will be remembered as a mission that combined technical excellence with important scientific discoveries. the detection of sulfur across diverse lunar locations, and the potential identification of mantle material near the surface represent contributions that advance our collective understanding. These findings will be built upon by future missions, each adding pieces to the expanding picture of the Moon's nature and history. The success demonstrates that space exploration remains a frontier where new discoveries await, where careful engineering and scientific inquiry can reveal surprises, and where the efforts of dedicated teams can achieve remarkable results. The knowledge gained enriches our understanding of our nearest celestial neighbor and the dynamic processes that shape worlds throughout the solar system.